Okay, let's continue. Okay, so we are looking at like problems other than prediction, right? So we before the break we saw semi-supervised learning, which is this idea of learning from examples, like both supervised examples and unsupervised examples, right? Like and then we looked at structure prediction, right? So now as a third problem, we are going to look at the problem of domain adaptation. Okay. Now, what is domain adaptation? Now, let's say we are interested in some prediction problem, which is a problem from x to y, and we have the probability distribution p of x comma y, right? Now, one way to write this probability distribution, the joint distribution, is as p of x multiplied by p of y given x, just by the chain rule, right? Now, in some real world problems, okay, so this part of the distribution, p of x, might differ from training to testing. Okay, I'll give you some example. Let's say we are interested in sentiment classification. Now here the idea is x is the review and y is either positive or negative. Okay, now I'm training my system to predict sentiment for movie reviews. Okay, in which case my p of x is going to be a distribution of movie reviews. After training the system on movie reviews, what if I want to use the system to make predictions about sentiment for car reviews? Okay, now the kind of words that we are going to see in car reviews are going to be very different. There's going to be some overlap, but it's going to be very different from the kind of words that you will see in movie reviews, right? However, this part, p of y given x, is still same. It is still the same prediction problem, given some bunch of English words, like I'm interested in predicting the sentiment, but it is different in the sense that the distribution of p of x, the distribution p of x changes, okay? To give you another example, let's say we are interested in object recognition. Okay, given an image, I want you to tell me what is that object. Now, I can train this system with very high quality DSLR pictures. Okay, now if I have to put it in a robot which has like very low quality sensors, or a mobile phone which does not have the same quality as a DSLR camera, right? Like so, now you're going to see the same apple or a car or any object, but the quality of the image is going to be different, right? This is another example where p of x is different. Okay, now here is an interesting problem. Like so, can I train a machine learning algorithm with DSLR pictures for object recognition and then adapt this algorithm to a possible situation where I have really low quality images from a very old phone, camera, like camera phone. Okay, now this is the idea of domain adaptation. Like so, now there are a lot of work in the literature on like how to transfer, like, or how to adapt your classifier to a different distribution. Okay, so that is domain adaptation. Any question? Okay, so now I can actually generalize this idea of domain adaptation. Okay, and that brings us to transfer learning. So instead of just p of x changing, like what if p of y given x changes, or like what if I get new y, right? Like so, the general idea of transfer learning is based on how humans learn. So like imagine how much time you took to learn your first video game, first ever video game when you were a kid, right? Like so, probably would have taken a few hours to recognize, like to get, like to become comfortable with the joystick and like some tricks to play the game, like, and like, so like the fact that you have to like gain scores, and the fact that you see the score in the top right, like, so your goal is to gain scores, and you should not lose your life because then the game is going to get, and so on, right? Like, so you have a lot of these things like that you're picking up in the first game, and think about how much time you took to become an expert in the second video game, right? Like, so you can easily transfer a lot of these ideas from the first game, and when you start playing your completely new second game, you already know that your goal is to not lose your life. You have to improve your score. You know how to jump. You have good handle of joystick and so on, right? Like, so we always take our knowledge that we have gained and apply it for the next thing that we want to do, right? Like, so now the same goes for any other task than just like video games, right? Like, so even your curriculum is designed in such a way that you learn all the basic math, and then you transfer that knowledge to some of the applications of math, like machine learning, right? So now, in the contrast, if you think about how we train our machine learning systems, like, let's say you want to train a neural network for classifying between dogs and cats. So what do? Like, so you take a randomly initialized neural network, do gradient descent, you have a classifier. Now I ask you to classify between different types of cars. Okay, we will not use the same neural network. Like, so we will start with a random initialization and again train. So in some sense, most of the ML algorithms are always training from scratch. Okay, but this is not at all a good solution for coming up with general purpose algorithms. So general purpose algorithms should be able to develop knowledge over time and transfer that knowledge to new tasks. Okay, now transfer learning is a very specific problem which focuses just on transfer. Okay, so to give you an example for transfer learning, right? Like, so I can train an image classifier. Okay, let's say a corn nut. This is a corn nut, and I put MLP on the top of it. Okay, it takes an image and the classifier which predicts the object, let's say. Okay, now after training this with lots and lots of examples for image classification, I can actually transfer this knowledge and design an image captioning system now. Okay, which given an image is going to give me a description about the image. Okay, so to do that, a simple solution, there are a lot of solutions. Like, the simple solution is you just copy the weights of this corn nut. Okay, so whatever weights you used here, which is trained for object recognition, you copy the weights here. Now on the top of that, right? Like, so we need a model to produce sequence of words, which is a caption, right? So we did not see LSTMs in this course, like, but LSTM is an example neural network, which is a recurrent network, which is going to produce a sequence of words. Okay, so in this case, like, what I would normally do is I first train for image classification, then copy these neural network weights here, okay, and randomly initialize this LSTM and train the whole system again. So we are doing initialization from the previous task, right? So this is what I meant by you should not use pre-trained weights in your Kaggle competition. Okay, so like, because then it is kind of cheating in the sense like you are using knowledge from some other task to make predictions for the current task. So then there is no way to control and standardize the rankings, right? So in fact, there are a lot of machine learning competitions where they have actually two tracks. Like, so there will be one track which would say you cannot use any extra data. There will be another track which would say you can use whatever you want. Okay, so for such tracks, you can do semi-supervised learning by collecting lots of examples, or you can do this kind of pre-training with other tasks, like, and transfer the knowledge and a bunch of other things. So this is transfer learning. Like, how do I design methods to transfer knowledge from one task to another? Is that clear? Any questions? Okay, so now we are going to generalize this even further, okay, and we are going to talk about the idea of multitask learning. So in transfer learning, like you jump from one task to another, then you don't care about the previous task, okay? But in the case of multitask learning, the goal is to design one algorithm to do many tasks. Like for example, one computer vision system, which given the image, can tell me what object it is, which is the problem of image classification, which can tell me where is that object located, which is the problem of object localization, like predicting the bounding box. Okay, but maybe I'll show you the example. Let's say I have an image which has a tree. Okay, now I can do many tasks with this image. Like I can do image classification, which will tell me, okay, this is an image of a tree. This is image classification. Okay, and I could do object localization, like which will tell me, oh, this is where the tree is. That is the second task. Okay, then I can do image segmentation, like which basically would segment things in such a way that, oh, this segment is one object. Okay, and the rest of the segment is another object, or in this case it's a background, right? So I can do image segmentation. I can do image captioning, like so for example, for this image I can say a lonely tree. Right? So now the idea of multitask learning is, can we come up with one algorithm or neural network, like which is what we are commonly using, to do all these tasks. Okay, now how would such an architecture look like? So let us see example in the case of neural network. In the case of neural network, like you will take the input x as an example. Okay, so you're going to have a bunch of layers which are processing things. Okay, now finally you can have different output layers. Like so I can have one output layer for task 1, another output layer for task 2, another output layer for task 3, and so on. Is that clear? Another example I can give is like a reinforcement learning agent learning to play many video games, like video game 1, video game 2, video game 3, and so on. Okay. Now, multitask learning is not always going to give you the best result. Okay. So if the games have similar learning, like similar dynamics, for example, then learning one game is going to help you to learn another game. But imagine games have contradicting dynamics, or imagine learning two tasks where one is kind of opposite of another. So now in this case, your signals, learning signals, are going to be contradicting, which means you cannot learn all these things together. Okay, so this is sometimes known as task interference. So sometimes task interference could hurt, which means your multitask learning solution might not be the best solution. You can, so for some application, you can just do one task and get really good results. Okay, so how to avoid task interference in a clever way? So that is the whole field of multitask learning. Okay, now to give you some comparison between transfer learning and multitask learning, right? So in the case of transfer learning, let's say there are two tasks. There is always transfer from only one task to another task, right? So you learn the first task, you have learned it completely, then you do the second task. You care about how to take knowledge from first task to another task. But multitask learning is much more general in the sense you can transfer knowledge from both T1 and T2 because you're learning them together. So T1 can help T2 and T2 can help T1. Okay, so in some sense, this is sequential transfer, but this is parallel transfer. Is that clear? Any question? Yeah.
Is there an interest to learn an easier easier form of a test to learn faster or better?
Okay. Well, I think that is not given in this list of 10 problems, but that is also another interesting problem. Like, so this is number 5. Like, maybe I'll just list it here without calling it number 6. Okay. So that is the idea of curriculum learning. Okay. So in curriculum learning, you will try to learn a curriculum, like where you start with simple tasks and slowly increase the complexity of the task. Now, if you think about how humans learn, right? Like we definitely learn based on curriculums. Schools and universities are best examples, right? Like so, like we don't teach you like partial differential equations to begin with, right? Like so, we start with very basic stuff, and then we slowly build upon things, right? Like so. Now, similarly, how can we design curriculums for machine learning algorithms to learn? Like there are many interesting questions here. Like so, first of all, how can we design a curriculum which is easy for machines to learn? But that is a very difficult task. Like an even more interesting question is, how can we come up with automated curriculum, right? Like so, completely automated curriculums, like, or how can we come up with another machine learning algorithm which is going to give curriculum for this machine learning algorithm, right? Like so, there are all kind of fancy research happening in this. Okay, well, maybe I should add this to my list of problems for next year. So now we can go to the next problem in the list, which is the idea of few shot or one shot or zero shot learning, like basically some shot learning. Okay, now this is based on the observation that most of these machine learning algorithms, they require thousands or like sometimes millions of examples to learn what is a cat and a dog. Okay, on the other hand, kids don't need to see million dogs to know something is a dog. You just need to show a couple of dogs. With just these 2 examples, they're already good to go, right? Like so next time they see a dog, they're going to shout, hey, there's a dog. Sometimes we learn about imaginary things, right? Like so, which we have never seen before, but when we see it, we will recognize, right? Like so, for example, when you teach what is an elephant to kids, probably you will not show a real elephant, right? Or tiger, for example, right? Like so, we never show a real tiger and say, hey, this is a tiger, like to begin with. So we will describe what is a tiger, like how does it look like, and we will show some pictures, and when we see it in the real time, kids recognize, okay, this is a tiger, right? So that is kind of zero shot learning. So humans do a lot of this, what I call as few shot or zero shot learning. Okay, like we don't need million examples to learn a concept. We only require 1 or 2 or sometimes just 5 examples. Okay, so there is different shades of this idea. Like so, when I say few shot, it means some examples like 2 or 5 or 10. When I say one shot, it means can I come up with a system which will learn a concept by just 1 example. When I say zero shot, I will not show you any example about a concept, but I will show you the concept and you should recognize the concept. Okay, which is very challenging. Like sometimes like you need extra input to do that. Okay, but maybe before we talk about this problem, right? Like so, why do you think machine learning systems are data hungry? Like, why do we need lots and lots of examples to train a neural network? Why can't we just show 5 examples and then have a really good prediction? Yeah.
Well, there are lots of models which are part of statistical estimations, so to have a good idea of what's the general law or problem, make them support.
Purely lots of example to generalize, but that is not completely true, right? Like human generalize without lots of examples. Any other reasons? Yeah.
or it's in the way they learn, like breaking distance, for example?
Yeah. So one of the primary culprit is our fundamental learning algorithm, which is the gradient descent, right? Like so gradient descent really takes tiny steps, which means even if I give you one example, gradient descent has to take 1,000 steps to learn that example. Okay, so which is a big limitation. But the thing is, we don't have any other alternative for gradient descent, like which is much more faster. Okay, so that is one reason. Like so gradient descent is slow. Also, transfer is a big issue. Like so, a lot of these algorithms that like we discussed in this course, like well, almost all of them, like we did not talk about transfer learning, right? Like so, they all start from scratch. But humans don't start from scratch. Like so, before recognizing a dog, a baby would have seen several thousands of hours of video by seeing the world, right? Like so, like we learn a lot continuously. Like so, we are like continual learning systems. Like so, like we pick up information, like we store the information, like we use it whenever we want, right? Like so, like for example, like when you start to go for a driving class, you have probably like 17, 18 years of knowledge. But we expect a neural network which has zero knowledge to start coming up with self-driving solutions, right? So how is that possible, right? Like it is not, if you think about it, it is not possible, right? Like so maybe it is possible for some problems, but not for all problems. Like for example, if you just take the game of chess, when we learn to play chess, we incorporate a lot of world knowledge. Like also when let's say when we play games like poker, like which involves bluffing, right? Like so, like we see the opponent, and by the reactions of the opponent, like by his eye, like his or her eyes, like or by the motions, right? Like so, you will make a lot of guesses, like which is very difficult to make just by looking at the cards, right? So these kind of extra social aspects and like common sense aspects are totally missing with current generation machine learning algorithms. Like so we need to have really good transfer learning algorithms, like if you want to go for few shot or one shot solutions. And finally, another issue is like most of the ML systems always deal with low level inputs. Humans don't deal with low level inputs. Okay, so take image classification, for example. The input to the image classification system is pixels. We don't perceive the world in pixels, right? Like so when I see this class, like somehow my perception is very sophisticated in the sense I see humans, I see chairs. Like for example, there are a lot of things that I would ignore, right? Like so, like after you go out, like so, if I ask you, was there a clock inside the room? You might not know. Okay, now you can see that okay, there is one clock here. Like, but if you have never seen the clock, probably that is not a very important thing that you want to notice anyway. So you would not remember it, right? Like, so we know how to filter things. We know how to abstract things into objects and so on. But for a neural network, there is no human here. There is no chair here. Like it is just a bunch of pixels, right? Like so such systems would require a lot of example to first develop the concept of humans, objects, chairs, and so on. Then they do the task. On the other hand, if you can design machine learning algorithms which can automatically deal with objects, then maybe it can be more sample efficient. Is that clear? Any question about few-shot learning? Any question in the chat? So chat is very silent today. Okay, so now we can move to the next problem. The next problem that I want to talk about is the idea of online learning. Okay, so far we had this traditional view of machine learning, like where I will give you a training set and a test set. You will train your model with the training set, and we will test generalization performance with test set, right? But online learning is a totally different approach where there is no separation between training and test. For online learning, because you are learning while performing. Okay, so imagine you trained a computer vision system like major image classification system. You deploy it as a service in the cloud. Okay, now it is getting a lot of queries. Now, as a company which is making this product, it is very important for you to have a system which is as accurate as possible, right? Like, so accuracy really translates to money, right? Like, so you want highly accurate models, which means you want to continuously learn. Like, you don't want to stop learning, right? Like, so you see one example, you want to learn. You see the next example, you want to learn. Now, that is online learning. In online learning, you make a prediction, you immediately learn about the prediction, and then move to the next thing, okay? There are many situations where online learning is the only possibility, okay? To give you another compelling example, the CERN experiment, right? Like, so like where they are looking for tiny particles, right? Like, so now in those physical experiments, they get terabytes or petabytes of data points flowing in every second, okay? So the experiment produces huge amount of data. But first of all, we don't have enough storage to store these data. Forget about computing, like we don't have storage to store these data. So now it is extremely important that as the data comes in as a stream, right, you learn something. So the standard machine learning task there is like is event prediction. Like you want to predict if there is any significant event that happened, which is what is going to support your experimental hypothesis, right? Like, so now which event is a good event? Like there are millions of events coming in every second. Which event is a good event? You have to learn online. You cannot collect this and like go back and process, because by the time you collect some example, like you already missed storing the most important example. Like, so you're spending millions of dollars to pick that one event, right? Like, so and if you miss that one event because you are collecting the data, there is no use with the experiment, right? Like, so that is another compelling example where online learning is desirable. So there are many other examples like where online learning is desirable. Like in the case of online learning, like there's no really distinction between training time and testing time. Like, so every second is both training and testing time. Is that clear? Any question? Now, typically when we design online learning algorithms, like people worry about what is known as regret. Okay, so regret is how much loss you incur because you did not have the optimal prediction. Like, so like when you do online learning, let's say this is the time, this is your performance. Okay, you want systems which would achieve good performance in very shorter period of time. Okay, so this system is better over, for example, this system, because the red system has this much relative regret, right? So basically there is this much error that you made which could have been avoided had you used the black algorithm, right? Like, so now typically, like when you have train test paradigm, you don't care about the training curve at all. Like, so all you care is really having the best possible output, right? In the end, right? Like, so if, for example, let's say playing video games. So there could be two goals for designing a video game playing agent. First goal is you do whatever you want during training. Give me an agent which will get highest possible score. That is traditional train test paradigm. Instead, the second possibility is I'm going to tell you, you have 5 hours to play. And in the end, I'm going to pick the best candidate based on the total score in this 5 hours. Okay. Now every game matters. Like there is no trial game. Like every game is a test game, right? Like you're learning, but you're also like performing. Is that clear? Any question? Yeah.
With minimize regret, because we don't want to be making false predictions immediately since we put our model.
Yeah, by minimizing regret, like I mean, you don't want to make false prediction. You want to reduce the number of false prediction as much as possible. Or in other words, like sample efficiency is a very important thing here. Like so, you really don't want slow learners. Like so, like for online learning, you want really fast learners. Okay, so now there is another type of interesting learning paradigm, which is the idea of active learning. Okay, so active learning focuses on situations where getting labels is costly. Okay, so when getting labels is costly, you have an agent which is trying to learn a task. Okay, you will have a bunch of data points. Let's say this is my bunch of data points. Okay, now an active learning algorithm will pick some data point and ask the human for the label. Now, let's say we start with all these unlabeled examples. Now, the idea is like every label is costly. There's a budget for you. You cannot overspend the budget. Now, can you tell me one heuristic? Like, how do I ask labels for the data points that you see here? What criteria I could use for this active learning problem? Yeah.
Well, you want the approach to take the most representative points of the neighborhood.
Yeah. So you want most representative examples to be labeled so that you have the big picture of the problem, right? Like so, a naive strategy could be, for example, first randomly pick this example and then try to pick something which is far away from this, and then try to pick something which is far away from these two both, and so on, right? Like so, and as you get more and more example, your performance is going to increase. When you reach the target, you stop. If you're going to ask label for all the examples, then you don't need to do active learning. So the idea is typically you would need examples only for, let's say, 5% of your data. If you need it for 100% or 80%, then you don't need to do active learning. Okay, now you can do more complex things. Like for example, you can take all these data points, do clustering, like come up with concept clusters and pick representative examples from the clusters and then ask for labels and so on, right? So there are a lot of interesting things that you could do. And active learning is one of the underexplored areas in machine learning. So I have not seen a lot of work in the recent years. Okay, so then I want to talk about the idea of lifelong learning, or also known as continual learning. Okay, so the idea of lifelong learning is to have one algorithm which can continually learn a series of tasks. Okay, now you can ask, what is the difference between this and transfer learning, right? Or what is the difference between this and multitask learning? So a lot of these learning paradigms are linked together, like so there is a lot of overlap, but it is just a practical setup which is different. So in the case of transfer learning, you do the first task, then you do the second task, but you will not care about the performance of first task while doing the second task. You just care about transferring from task 1 to task 2. In the case of multitask learning, you want to do all the tasks well, right? In the case of lifelong learning, it's a combination of these two. Like it's kind of sequential multitask learning in the sense, like you will learn task 1, okay? Then you will learn task 2 sequentially, okay? But when you are learning task 2, you want to make sure that the performance in task 1 does not degrade, okay? So the fundamental problem in designing lifelong learning systems is this problem of catastrophic forgetting. Which is basically, while learning the second task, you might forget how to solve the first task. So why is this happening? Like, for example, when you use gradient descent, right? Let's say you have a simple neural network. When you do gradient descent for first task, you learn a configuration. when you start doing gradient descent for the second task, you are moving away your parameters to the second task, which means the current network might not be a good enough network for the first task, right? Like, so now how to solve catastrophic forgetting is the fundamental problem in lifelong learning. But if we can solve this problem of catastrophic forgetting, then we have a really powerful general purpose learning algorithm, okay? So such a lifelong learning system can actually retain the knowledge that it has learned. It can do transfer learning by transferring from the old task to previous current task. And it can even do backward transfer. Like, so while learning the current task, it will have a realization about the previous task so that it can do better in the previous task. Yeah.
How different are these tasks we are trying to learn?
Okay, that's a good question. So if the tasks are very similar, then the problem setup is easy. But the tasks could be very different. Like, so for example, like I could have, like, we can go back to the image example, right? Like, so I could do image classification, image segmentation, object localization, foreground, background separation, like, or image captioning, or visual question answering, right? Like, so I can do a variety of tasks. Like, so, like, it could be similar or it could be really different. Yeah.
I understand that through neural networks, we are trying to recreate whatever the brain is trying to do. And it's also understood that the brain uses different portions to learn different things. Is that somehow related to?
Yes. So there are methods which talk about modular neural architectures, like, so where the modules correspond to different expert modules in the brain, right? Like, so, like, that is definitely one interesting exploration for a good algorithm. Okay, so finally, I want to talk about the idea of meta learning. Okay, or sometimes also called as learning to learn. Okay, now this is taking the whole problem of machine learning to a meta level. So can I come up with a good learning algorithm which can learn tasks in an efficient way? Okay, so in other words, this is related to continuous learning but a little bit different. So the idea in meta learning is I'm going to have train and test. Okay, but my training and testing are not on examples, on tasks. Okay, I will give you a bunch of tasks, T1, T2, T3, and so on. Okay, each of these tasks themselves are going to have some training set and test set. Right? Now, you can do whatever you want to do with this set of tasks. But after learning from these tasks, I'm going to test you with a new machine learning problem, task 4, which has train and test. Okay, I want you to do really well in this task with very few examples. Is that clear? So in some sense, we are learning a higher level, like a meta learner, which will help us to come up with efficient learning algorithms. That's why it's called learning to learn. Okay. Now, there has been a lot of progress in all these problems that I discussed today. So again, these conferences that I mentioned, like, you go there and check their proceedings, you're going to see hundreds of meta learning papers, lifelong learning papers, transfer learning papers, and so on. Okay, like, if you want to learn more about these things. And I think there is a new course coming up at UDM next semester, which is going to cover some of the problems that we discussed today, like meta learning, lifelong learning, transfer, and stuff. Like, so, like, I don't know the name of the course, but it is going to be taught by Professor Irina Risch. Like, so you can check for her most recent course. Like, so there's going to be a new course. Yeah. So I think we will stop here. So I would like to thank everyone, like, so, who made it to the last lecture, especially the most sincere batch of students, like, who showed up for every single lecture. Like, so I really appreciate it. And I hope you learned something useful in the course. Like, I also hope to improve the quality of this course every year. Like, so if you have any feedback about the course, you can come talk to me directly, or you can put it in the anonymous Google feedback, the Google form. Okay, so both are fine. And one last reminder, please go do your course evaluation. So we still have 50% of you not done with the course evaluation. So that is very, very important. And hopefully I'll see you in some other courses next year. Thank you. Any questions? Well, is there any question in the chat? No, thank you everyone for your feedback. Okay, so I think if there are no more questions, we can stop. I still have my office hours, so if you want to